everyone, my name is Alexey and I work at Positive Technologies. The previous speaker talked about the unit, about the department where I work. I test various hardware solutions, I participate in various tournaments. I am a winner of Flare Run competition. I do research, I speak at conferences. At my website you can find lots of my publications. Recently I've been publishing on checkmate related stuff. And today I'll talk about GD32 microcontrollers. They are produced by GigaDevice, a company that was founded in 2005. They first started with NOR flash memory, but around 2013, 2015, they started manufacturing their own microcontrollers based on ARM Cortex-M architecture. They also have a lineup of products that's based on RISC-V. Over here you can see the lineup of their products. They have lots of different microcontrollers with varying performance and architecture. Some microcontrollers are special purpose. GD32 PR for work with fingerprints. There is another one that's used to work with Wi-Fi, Bluetooth, and other wireless protocols. But today we'll talk about general use, general purpose microcontrollers. When manufacturers design their own hardware, they want to protect their firmware, the encryption keys that are built in, and various unique algorithms. Microcontroller manufacturers to take care to protect the products from readout. For instance, in STM they use RDP, in NRF protect. In GigaDevice this is security protection, and today I will talk about the vulnerabilities and security protection by GigaDevice, but I'm going to talk about RDP or readout protection because this is a more general and a better fitting term. Although the technologies bear different names, inside they look the same. They have several levels of protection, and every level has its own restrictions. Level 0 means there are no restrictions. The first level of protection locks access to flash memory in debug mode, and usually this level can be downgraded to level 0 with total loss of flash memory. Level 2 is the highest level of protection. Usually all the debugging interfaces are disabled. Usually you can't boot from RAM or system memory, and this is an irreversible level that can't be downgraded. The level of protection usually is determined by a byte that is stored physically in the same cells of flash memory where the main firmware is stored, but access to this byte is achieved by different means. My presentation will contain two parts. In the first part, I will briefly describe the existing attacks on these technologies. We need to first get an impression of how difficult it may be and what the simple attack ways are. And I will be referring to some of these attacks later when we get to the second part of the presentation that will be devoted to our research of vulnerabilities. I'll describe the process. I will be referencing two main firmware protection research. One was conducted by Johannes Obermeier and this is a research around the microcontroller that's installed on your on your badges. This research covers security, downgrade, debug interface exploits, and several other techniques. There will be many links in this presentation. Later I'll explain where you can download the papers from. I will skip some of the overview vulnerabilities to get to the main part of the presentation quicker. The first technique that Obermeier and Tashner demonstrated is called bootstrapping. Like I said, the RDP1 SRAM is still available under debugging, so you have to remember about that and never keep intermediate keys or any sensitive data in the memory. But even if you do this, with this technique, you will still be able to get intermediate states of SRAM all the way to individual instructions execution. If bootload is it follows a signature verification algorithm or a hash sum CRC32. If we can get an intermediate value of this hash, then we'll be able to restore the firmware. Or another example, this is a more challenging technique. Here, the researchers acidify the crystal, the chip. They get access to the crystal. On the right, you can see the photograph where all the chip is mapped out. It has the flash module and flash cells, and the bytes that's responsible for protection is stored somewhere in these on these flash cells. They use arrays of certain lengths to change the value of the bits, and this is how you downgrade the protection. I will not discuss this technique, but this is the way you can dump the firmware from your badge. This is a more recent research. It was conducted on STM32F0 in its Chinese analogs. The research studies a number of vulnerabilities using the debugging interface, several invasive attacks, and power related attacks. We'll skip that as well, but we'll stop here. You can see the flash memory controller. We access the controller via several buses. The core can have access to the controller via the instructions bus and the data bus directly. The controller is also connected to the HP bus, and this bus carries various masters, including the kernel and DMA engine. The vulnerability here is that with the use of DMA, data can be transferred from flash memory into static RAM. So protection, there was no, this path was not secured, and this protection could be bypassed. Simpler vulnerabilities included no locking of the instructions bus. It wasn't locked every time, so you could retrieve some information from the bus. Another example of an invasive attack, I will be referring to it later, that's why I'll talk about it now. Some chips, microchips, are based on multi-crystal architecture, and in here you can see a large crystal from the bottom. This is the logic crystal, and a smaller crystal is the flash memory crystal. They are connected with wires. So researchers removed the upper layer, and they realized that QSPI protocol is transmitted via these wires. At first boot, certain factory settings are read from the flash memory. After that, bootloader is initiated, then option bytes. And this is the area where this protection byte is stored, and after that, the obfuscated firmware. Obfuscation can be removed easily. You just reverse the algorithm of substituting or changing the words and bits. But researchers also realized that all it takes is to change 2 bits, and this is how you downgrade the security level. The last attack that they considered is the power glitch. Using a glitch, you can zero out the processor, but the static RAM remains intact. So they prepared the code, they ran it, and they retrieved the firmware. Several more links will be included onto the slide. On the first link, you'll find an overview of well-known vulnerabilities. The second publication is on glitch, power glitch, and the last 2 are also dedicated to the power glitch vulnerability of various microcontrollers. Let's move on to the main part of the presentation. I'll talk not only about our own findings, but also I'll describe the process of research, covering all its failures and successes. It all started with this sensor that you have already seen. This is the air quality sensor. The red box here, shows you the debugging interfaces, SVD and the reset pin and power pins. I understand I will be repeating something that other speakers have already said, but first we connected a debugger to these pins. We found that J-Link utilities, although debugging didn't work via them, they could read the DPRDR register. We used a logic analyzer to see that the J-Link utility is trying to read DPRID in various ways, and one method it used was NRST with an NRST pulled down when the chip is pulled down. We checked it manually, then we modified the config for this chip so that we could use it as well. At that time, we still didn't understand whether what we were seeing was a locked chip in RTP2 or maybe it's just a pin reconfiguration at startup. A couple of words about security protection by GD32. As I've already explained, there are 3 levels of security or protection. They are set by the option byte security protection code, and everything else is just like you find in all other microcontrollers. First thing, we wanted to understand what was available to us in the reset mode. I tried to read and write the memory. It read out as 0 and changes didn't affect it. Flash read also returns zeros. Peripherals read would always return the reset value as was expected as per reference manual. When attempting to debug, they worked in accordance with the documentation, and for instance, the debugging bit could not be retrieved immediately, but if senior bits in the same register, you would write the documented key, then the bit would present itself. And the same worked if you wrote into the comparator register. But at that time, we were still not sure whether it was a chip lock or not. We decided to buy microcontrollers. It would be wonderful if we could get dev boot, but it was difficult to lay our hands on them, so we bought the MCUs. We found this whiteboard adapter. It's a network adapter for a refrigerator. Would you believe it? It's a great chip. It has everything, including an oscillator, an LED. It has debugging pins, but we still had to work on this dev board a little bit. We got the lanes that were controlling the booting, and we also added two pins that did not have any function to use them later. So as we ran our check, we were almost sure that it was an RDP2 lock, because our locked chip worked just like our target sensor. What does it mean? It means that we'll not be able to dump the firmware, but otherwise I wouldn't be speaking here today, would I? So since SWD is available in the reset mode, an idea occurred to exploit that. So SWD is available during reset. So maybe if we change the reset signal to disconnect, to disable the debugging interface, it will take some time, and we will have that much time, that window for a race. To exploit it, one needs to understand the SWD protocol. It's a debugging protocol. It has two lines, the input-output line and the texting line. It allows you to read and write and to debug. The protocol is described in the specification. So which registers can we read and write using this protocol? We have debug port and the access port. Using a debugger, we connect directly to the debug port, and this one will provide us with access to various access ports, including memory access port, which is used to access the memory. UDP and AP has different registers. For instance, ID code, which is an identifier of the debug port. It's the value that we were trying to read using CD in the very beginning. An important register is control stat. I will explain it later. The select register allows us to select the relevant access port, because there may be several of them, and a specific memory bank in it. And the RDBuff is used to obtain the read output, the read of the last operation of access to the access port. The read of the access port operation data is showed with a delay of one operation. During the first operation it will be indeterminate, then during the second transaction we will get the result from the previous operation. As to the access port registers, the memory access port, there are more registers than the ones listed here, but we need to know three of them. CSW allows us to configure the operation to indicate the number of bits in this operation, like 32 or 16 or whatever. The address register allows us to set the transfer address, and the data read-write allows us to read and write. Control stats register. All we need to know is the 4 senior bits from it, the specification of the debugging. It determines 3 domains. In the power domain, there is a power domain that's constantly on. There is the debugging power domain, and there is a system power domain. The first one includes the debug port because it must be on all the time. The debug power domain includes various debugging units, including access ports, and the system power domain includes core, static RAM, etc. Enabling disabling the debugging and system power domain, we use special registers. There is a request register for all of them. You make it a logical one, and after a while, the debug port should respond with a confirmation. It means that we can try to read some memory or from memory. We need to perform the following 8 steps. To do it, first we prepare, we reset the interface. Some debug port can work with several protocols. So first we need to configure and select one protocol using special sequences. After that, we read the ID code. It is a mandatory step for debug port to operate, but in fact it depends much on the implementation. Next, we enable system and debug power domains. We select the 0 bank of memory access port. Then we configure the operation. For instance, we want to read 32-bit without the target address increments. We write the target address, then we read the data read-write register, and then the output of read we get through RD buff register from the debug port. The first attempts, and I forgot to tell you that since SWD works under reset, everything apart from step 7 can be done in the reset mode. And when we try to fit the command into rest window, into the race window, all we need is to perform this 7th step. So we made our first attempts with libjlink and the jlink library. You may think that this can be easily achieved and it should work fast, but to control reset in sync with debugging lines turned out to be a challenge. There is special IP to change the reset signal, but since all of this is operating via USB, there is big latency between the packets. So we worked with the reset pin with our hands, and we found out that we did receive adequate responses for some of the packets, so we did not despair, and we proceeded. It became clear that we needed a microcontroller. I selected RP2040. It's a Raspberry Pi microcontroller. It has 2 cores, Cortex M0 Plus, and its frequency is 133 megahertz, but it can be accelerated to 250, and it clocks nicely at this frequency. The main feature of this microcontroller, in my opinion, is the PIO block, the programmed input-output block. Actually, RP2040 has 2 PIO blocks, 4 state machines each. Each state machine works independently of the other and independently of the main cores, and it executes the input-output instructions. PIO can execute many different or run many different protocols. Sometimes it can even replace FPGA. I'll show you some examples where it is used. For instance, in hardware security, especially in glitches, like Pico Fly, that's a mod chip for Nintendo Switch. It uses glitches to bypass secure booting. It's an example when RP2040 can replace FPGA, because before PicoFly there were other projects like Everfly. They used FPGA chips by Lattice for glitches. Chip shooter Pico AMP is a chip device to launch electromagnetic fault injection, and the Starlink chip, mod chip, it also uses a power glitch to bypass secure booting. RP2040 offered another bonus. It has a pickup probe, a sensor, a probe, so we could take its software from a project and the C functions as well to control these programs. On this picture you can see how it worked, more or less. So we've got a Raspberry Pico to the right and our test board with a logical analyzer connected to it via this intermediate board. So with this solution, we implemented the algorithm that I described earlier, and we controlled it over USB UART. We met with success. Like I was saying, first we prepared the initial configuration that did not depend on reset. And in the last operation here, you can see me writing the target address into the register. Then I changed the state of the reset signal, and then after a short period of time, I'm trying to read the read-write register. At the bottom, you see this log continued. You can tell that after I've changed the reset line again, and I'm trying to read RTBF register, I'm receiving a value, and this value looks very much like the address inside Flash. This is how I did a snapshot of all stages in memory and SRAM memory, and it was it, because you could see stack, return addresses, initialized addresses, etc. So what are our findings on this vulnerability? Oh, and by the way, we can also write into static RAM memory. Like, what are the results? We can read write RAM. We also tried peripherals. This memory can also be read-write. We tried to read option bytes, and we were like almost 100% sure that our target is locked to RTP2. As to write, it seems like this is a useless function, because after writing we reset the state of the signal, and after that the chip will not work with what we wrote into static RAM. But still, some ways to exploit this vulnerability can be found. We can adapt the cold bootstrapping technique that I described at the start of the presentation, but in some cases you don't even need cold bootstrapping. It's enough to get a snapshot of static RAM at a certain period of time, just like we did it with WB firmware. We uploaded it, and it turned out that in static RAM, you could see the decrypted, and this is how we retrieved the firmware. Next steps. We wanted to test this vulnerability on other microcontrollers, GigaDevice microcontrollers. There are many families of GigaDevice MCUs. We needed to optimize our work somehow. So our solution was to group different families of microcontrollers along certain criteria. One of the criteria that we chose is a shared manual or common manual. I'll explain what it means later, but in terms of sourcing, at the start of this research, it was difficult to get the chips. In ChipDeep, you had to wait 4 to 6 weeks. It was okay, but we wanted to start working faster. Most chips were found at AliExpress. They delivered to us within a month, but some we had to buy just a month ago in local shops. Now, the way we grouped the families, if you look At the GD32 there are 7 families of those chips in high performance. They're shown here in purple, but all of them apart from 403 have a shared menu, so we decided it was enough to take one microcontroller from this family, from this group, and that's what we did. So we have this set of chips. It's a photograph of our chips so that you can see all the data there. These are the opened up chips. You see more of them are shown here than on the previous slide because we also tested the RTP1 lock vulnerabilities. We needed copies for RTP1 lock. This is the success table. The vulnerability worked in the E and L family chips. This is an RTP2 vulnerability. That's why the chips listed at the bottom of the slide, we couldn't test them for it. As to the second vulnerability, when we were exploiting wiring board, we found out that the flash memory log is triggered when a debug domain is enabled. So we could disable it, reset the chip, and unlike STMs, the log would be zeroed out, and the microcontroller firmware would work fine at the next iteration. We thought that how about doing it in runtime? Enable and disable the debug domain, reset the log, and maybe it can help us to bypass the RTP1 protections. And it turned out that yes, that's how it worked. And we can use this algorithm. You use a debugger to load firmware into static RAM. It will be waiting for our signal, and after the signal is received, it will dump the memory, the flash memory content. Then we reset the debugger port bit. Then we signal somewhere to begin dumping, like I said, and then, this algorithm works, as we learned from our experience. This is the result. All of the microcontrollers that we bought proved to be vulnerable, apart from the L family and the F330. And the third vulnerability. Here we go back to the F series that we could not bypass in the beginning. So the vulnerability didn't work with the F family, but we also realized that with the power off reset, there is a race window where SWT still responds. And this window is larger, much larger, 1600 microseconds compared to the E series, where the window was only about 20 microseconds long. However, at first we didn't quite see whether this is useful or not, because the memory is still not initiated. It's in a non-initialized state. It doesn't contain anything interesting. So I tried to play with this race window. I manipulated with the VTOR, but it seems like after some initialization, it takes the reset value anyway. I tried to debug the core, and I also failed. I experimented with a similar chip in RTP0, and even at the startup initialization, nothing interesting or exciting happened. And then I decided to run the first voltage glitch, or power glitch, in my practice, and I started with power analysis. This is the oscillogram. You can see here that there are some surges, and if you count the distance between them, you'll see it's 32. 32 is degree of 2. Whenever I see degree of 2, I'm happy. Let's take a closer look at the beginning, right after the startup, several microseconds apart from the startup. You can see the first 2 surges or hops, then 1.8 milliseconds. For 1.8 milliseconds, nothing happens. But it's interesting that the race window is exactly that long. Then 2 more surges, voltage surges, and we see the same pattern of 32 surges. Now let's zoom in again. You see some periodicity in this chart. More voltage surges, maybe less visible, but you can still count them. You can count the intervals. 64 again, the degree of 2. Is this a coincidence? I don't think so. So how do you interpret these results? And I will be referencing now the research where the authors obtained access to SPI protocol. And they explained that when during the power run, at power run, first some factory settings are read, the 32 bytes in the beginning. They are the ones that we see in the beginning, with the smallest interval of 16 bytes. And after that, bootloader is read. After that, option bytes, where the protection byte is stored. So, and this is something that we would like to capture. And in the end, the firmware, the half of the firmware, 32 kilobytes or 32 pages. So all of this corresponded to our power analysis. This is my first glitcher. I'm still using the same Raspberry Pi Pico. I added several MOSFETs to it. One is responsible for power supply, to reconnect this, the chip to reset it. The other MOSFET is responsible for the glitch itself. I selected the same one that is used in the Whisperer Lite chip. Here you can see on the screenshot the glitcher in action. This is when we have reading option bytes. To the right on the screenshot you see the form of my glitch, the glitch shape. Well, actually it did not help. I went through several read offset parameters. During read I changed the size of the bus to change the glitch to make it less powerful, but still it proved to be an interesting tool, and I glitched NRF just a couple of days ago using this glitcher, but my presentation is not about NRF. So after this failure I decided to do another attack through the debugging interface. I have already played with the core. I tried to do something with static RAM with a flash memory controller, and nothing worked out. But you can see on this block diagram that there is still a lot of peripherals available. It's not clear whether the peripherals are engaged at initialization, but we can go one by one. We can start with pins. Here is the code for initialization of the GPI module. At the top you see the log of the analog analyzer. So I'm using debugger to set the bit, the signal goes up. When I reset the bit, the signal goes down. So we understand that GPIO works just fine at initialization. Then UART. You can tell that during configuration the line goes up, The pull-up settings are working, and then when I write F into the special register, we see that F is written in the UART line. Next, the DMA engine. As we have already seen, it's a good exploit opportunity. So I decided to first write something into static RAM. I configured the DMA engine for this value to appear in UART, and it worked. Right after I started the DMA engine, we saw this value in UART, the value that I wrote. After that, I wanted to write, instead of the static RAM address, I wanted to write a flash address. I did not believe much in success, because when this is happening, the flash memory is still not initialized. It's still not read into internal cache. And RTP2 log, well, it should not be working, right? Here is the result. The result was quite curious. First, I thought it didn't work, because right after initialization, no data appeared in UART. But then I noticed that there is data. They are written about 18.5 milliseconds post-initialization, and this is the time of the startup initialization. And we know about this period of time owing to our power analysis. And you can see the stack address. After that, you see the vector reset address and some other vector that repeats itself. So, okay, on the microcontroller, we had the test where I knew what data it contained. I compared the results with what I got via UART, and I got my confirmation. I saw that this vulnerability was active. This is the success table. All the F series chips are susceptible to this attack. Now, I'm discussing here the EL and F series on the slide. If you open the reference manual and you read the flash memory controller chapter in EL, you read that when executing instructions, we have waiting time. So you may conclude that either flash on these in this series is so fast, or the cores are so slow that there is no need in caching. So option bytes assignment can be read at every reset. It will take about 20 microseconds for initialization, which is quite acceptable. Therefore, we have a small race window on each reset. In the documentation of the F series, you write something different. It says that for some of the flash there is no waiting time, but the other part of the flash has a long waiting time. Probably this is achieved through the use of cache upon the first boot of the chip. First, some inner internal flash is read, and also bootloader and option bytes are read. This takes quite a long time, about 18 milliseconds. If this were the case for every reset, it wouldn't be acceptable. So this cache survives resets. And because option bytes are also cached, SWD is no longer available at other or subsequent resets, but there is a big race window on the power run reset. This is the success table. You can see that all microcontrollers that we bought, one or another, are vulnerable. So here are the results. I got lots of experience in security of microcontrollers. I found a new technique to bypass the readout protection, and we reported 3 vulnerabilities to GigaDevice. Conclusions. Some implementations of readout protection technologies are far from being perfect. You have to consider this when developing your own hardware solutions. Maybe you will restrict physical access to the debugging pins, or you will control the accessibility of the end device to the user, or come up with something else. Well, in any case, your defenses will be broken sooner or later, so you have to prepare for it. You can get in touch with me on Telegram. Please write your questions and ideas or comments and remarks. If you know where GD32 microcontrollers are used, please let me know. And as I promised you, here is the QR code. It should contain this presentation, and that's it from me today. Thank you for listening. I'm ready to take your questions now. Thank you for the presentation. Can you say a couple of words about the whole process of vulnerability research and how the vendor responded? Well, I can't tell you much because I wasn't much involved in the process. I only did the research and wrote the reports. As far as I know, initially the vulnerabilities were reported via the form on the website, but we didn't get a response. And then we contacted the Chinese CERT, and then it's been, I think, 2 months. And after that, we received some reply from them, but it was pretty vague. Okay, impressive. How long did it take you? And what was the most difficult part of it? Well, it all started sometime in March when I got my job at Positive Technologies. I think that we found the first vulnerability within a week. This is the vulnerability with the static RAM readout. After that, we had to wait for new microcontrollers. It didn't take us long to run the checks on them. I think in just a day we checked the microcontrollers for this vulnerability. The second vulnerability I presented, well, actually we found it simultaneously with one other vulnerability. Basically, you can say that we even found it before the first actual vulnerability. The F-series proved to be the greatest challenge. They were special because reset was available, SWD rather was available in the reset mode, but I didn't know what to do about it for a while. But I read the papers once more. I decided to try the DMA engine, and it worked. Well, I think, well, obviously it wasn't full-time, but I've been going through failures for about a month. And after you make a discovery, it takes a couple of days to validate it. Okay, thanks. And one other question. The DMA engine, if my understanding is correct, the CPU on the bus is the master. Yeah, the core is the master. It's difficult to program the core, the DMA transaction. Do you have to write the structure somewhere? No, it's not very difficult. Well, there are options. You can configure the 4 registers. The size of the transaction, the source, the destination address, and the register that tells you what this transaction is, memory to memory or memory to periphery, and to run it. So this is all of the code that I had to add to this previous page for it to work. But on this bus, you can't select the address of the device that you communicate with, right? You have to configure the device you want to talk to. In ART, for instance, you have to enable that this is the DMA link that we're going to use for UART. As the destination address, you state the memory I/O register of the byte where symbols assume their value. No, wait. I'm going to find the right slide. So I'm writing F into the address. And the pin line of the DMA, I use the same address as destination. And this is how you set where do you want to use the DMA. But it's a tiny driver. It's a tiny driver on the back of your envelope, right? It's basically you configured a DMA transaction. Well, yes, in a way. This code worked on a different controller without any changes. And the third microcontroller needed a special approach, but generally the number of registers did not change. Thanks. Hi, I wanted to ask a question. You said you couldn't find or buy the debuggers for GigaDevice microcontrollers. If I'm not mistaken, they are pin-to-pin compatible with STH. So what was the problem? To buy debuggers for ST and use them on GigaDevice? Well, I don't know. Those network interfaces for refrigerators, we already had them. We could just take them off the shelf. To find dev boards for STMs, probably it would have taken us a day, but thank you for this idea. Next time, we'll bear this in mind. Okay, thank you for the answer. Thanks for the talk. It was quite exciting. Do you have any ideas why the glitch attack failed? Yes, I have some ideas. Not enough attempts. Something was missing. I was thinking about my upcoming vacation. I wasn't trying hard enough. Maybe one day I'll come back to it. As an idea, I now realize that maybe I should adjust the initial power run on the microcontroller, because I saw this done by other researchers. And there is also a shunting resistor. Maybe I can play with those parameters. And initial voltage, maybe I can play with that. It's something that I did not do for this